Welcome back. This is probably going to be the penultimate video in our week 2 series, and we're finally, I think, ready to discuss our periodic trends. Okay, periodic trends. Okay, I've listed what those are in my title video, but I'm just going to go straight to the point. The first one we're going to look at is atomic size. I've also heard people say it as atomic radii. Okay, this is the first one we're going to look at. Okay, and any of you who have ever taken any math class and you've talked about circle, you probably have heard the word radius, which is basically, I don't think that changes because you come to chemistry. If this is the center point of your circle, this whole thing is your diameter, and this part right here is your radius, right? So radius is basically diameter over 2. That has not changed because we crossed bridges from mathematics to chemistry. We can't just change concepts. Okay, it will still be the same. Okay, so every atom, okay, if this is the element, okay, really bad circle, by the way, I don't think a circle looks like that. If this is the element, it's got bunch of atoms. Remember I said it's 6.022. Again, you do not have to ever memorize this number. Okay, all right, and probably when we start doing real math, I'll probably show you how to input this into your calculator if you didn't already know. All right, but that's beyond the focus of this. So if we just pick one of those, okay, a single atom. Remember I said what happens in one atom is photocopied into all the other remainder of the, let me go ahead and make some effort here and do a better job completing it. I still don't think I did a good job. Anyways, that's what my circular atom looks like, and these are your shells. Remember, an atom has nucleus. I think I'm going to just get rid of this altogether and redraw it. For some reason with these tablet pens, it's very difficult to draw these circles, even though you can be, but I know this is really used for making artwork. I don't know how people do that. So anyways, I'm just looking at a single atom, and we know inside the atom's nucleus has got the protons and neutrons, and I think here you have your shells. Okay, I'm going to draw two different cases just to explain my point. Okay, protons and neutrons, and then I'm going to draw one with just one shell. Okay, I mentioned the idea of radii. Okay, the radii is for this particular atom, which got 2 orbitals around it. Okay, this all the way here is your radius. However, for this, it's this. So how many orbitals does a atom has, okay, governs how big it can be. Obviously between these two right here, okay, you probably guessed it. I'm going to pick a different color. Which one do you think will be big? Well, it's not that straightforward question or answer, but for now let's go with this one, okay, because it's got the biggest radius of the two. Okay, but I wish chemistry is that simple, but we're going to see in the future workouts as I'm writing that it is not as simple as math, that something with big radius is always going to be big in size, something with small radius is always going to be smaller in size. All right, but this is kind of what we're trying to get into. Okay, now I'm going to show you a slide. Okay, all right, I hope everybody can see it here. Okay, I'm going to put all this on the screen. Okay, atomic radius, if you look at the periodic table holistically, okay, atomic radius typically, when I say the word typically, I literally mean it, because there are some exceptions, and we probably will not get into those exceptions because then that will cause probably more confusions. So we're going to look into only cases where there is no exception. Okay, atomic radius typically decreases across the period, which is left to right. Okay, period is rows, groups or columns. Okay, period, left to right. Okay, and then atomic radius typically increases as you go down the group. Okay, for example, if you have beryllium, carbon, nitrogen and oxygen, now these are ground state atoms. Okay, these are not ions, these are just ground state atoms. If you see boron is first, and as you go from left to right you see oxygen. So which one is smaller of the two? Well, of the four, oxygen is the smallest and then boron is the largest. Okay, and then if you look at the next four elements, hydrogen, lithium, sodium and potassium, well, hydrogen is at the very top and potassium is at the very bottom in the same column. These are all in the same single column. That means atomic radius increases. And why is the trend? Okay, now let me come back to my screen right here. Okay, I said boron. Okay, I had boron, carbon, nitrogen and oxygen, and this is what I had. Boron is bigger than carbon, is bigger than nitrogen, is bigger than oxygen. Okay, if you write the electronic configuration of boron, okay, it's I believe it's if you go to the periodic table, okay, I think it's atomic number 5. All right, so that means it's got 5 electrons, right? So it's 1s2, 2s2, 2p1, right? Whereas I'm going to look at oxygen, or actually let me do it for all of them. Carbon is 6, so it's 1s2, 2s2, 2p2. Okay, nitrogen is 7, so it's 1s2, 2s2, 2p3, and oxygen is 8, which is 1s2, 2s2, 2p4, right? What do you see is common among all 4 of these electronic configurations? Let me choose a color so I can box them. Okay, now if you see, they're all in a row and they all have this part in common. So it is not these that govern the size of these as to why boron is bigger and oxygen is smaller. It is this right here that governs the size. That's why I said, unlike math where simply the radius is not just governed by how far the orbital is from the center, well, they all, if you look at it, they all have 3 shells around the nucleus, so they should all be the same size, right? Right? Do you see what I mean? So if this were to be the nucleus, this is the first shell, this is the second shell, it's the third shell. They all have that. So if it is this is the radius that governs how far that outer shell is from the inner, well, then we should say boron should be same as carbon, should be same as oxygen, should be same as nitrogen. Well, that's not the case. Clearly, oxygen is the smallest of the bunch and boron is the largest of the bunch. Why is that? Well, the answer is already in front of your eyes. You see this p orbital has got only 1 electron. We are adding 1 more electron into the same p orbital for carbon. Okay, for when we come to nitrogen, within the p orbital we're adding a 3rd electron, and here we're adding 4. Remember, p orbital can hold a maximum of 6, right? Now maximum does not mean it's going to be, there's going to be some fight. And let's say you're walking across Midway campus, where the chances of you bumping into people's head is slim to none. There's more space. Whereas if you're in Times Square on New Year's Eve, chances are, well, everybody's going to step on everybody's feet and everybody's going to get pissed off because someone's stepping on your foot and they're not apologizing. Well, welcome, that's New York, all right? So if any of you New Yorkers here, I'm sorry I didn't pick on New York. New York is a beautiful state, all right? But what I'm trying to say here is just take my example, okay? Don't think I'm criticizing New York. But New York on a normal day is chaos. New York at Times Square on New Year's Eve is chaos times 10. All right, so here we got 1 electron in boron, whereas when we go to carbon, we're pushing 2 electrons into the p. So what happens is, if there's 1 electron versus 2 electrons, they're fighting with each other for space, okay? And when we have 3, by the time we get to, there's 3 electrons, and then when we get to oxygen, there's 4. The more the people, more the chaos, and that is simply what's happening here with these 4 electrons, okay? So if you notice, and when more electrons fight, they do make, don't ask me why, I don't want to go into further explanation, just take my word for it that there's more electrons, there's going to be some electron repulsion, and which also would contribute, and nucleus loves electrons. The more electrons you have, there's more what is called a nuclear pull, okay? Nuclear pull. Oops. There's nuclear pull. More electrons you have, the nucleus pulls the electrons towards itself stronger. So that's why oxygen is the smallest of the bunch and boron is the largest of the bunch. And you can do the same trend for the other set where I shown hydrogen, lithium, sodium, potassium, I believe, and I showed hydrogen is the smallest and potassium is the largest. That's because we will be comparing completely different orbitals. Valence orbitals will be completely different. Here if you see, they're all 2s, 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 2p, 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 whereas with the hydrogen, lithium, sodium and potassium, the orbitals themselves are different. That means you have an extra orbital in between, which means the electrons are shielded better, okay? Maybe, okay, let me draw a picture of it. So this is what I'm saying without any particular example. Say this is the nucleus containing protons and neutrons. Say if this is hydrogen, which has got only one s orbital, okay, by the time you get to say potassium, and if we can bring up the periodic table really quick just to show you, it's in row 4 of the s band, right? That means if this were to be the nucleus, okay, you got to get through 1s, 2s, 2p, 3s, 3p, and then 4s, right? Right? This is the 4s. This is 1s. This is also, if you write the electronic configuration for hydrogen, is 1s1, whereas potassium is 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. While they all have, okay, well, I shouldn't have compared hydrogen. Let's say maybe lithium, okay? That might be a better way. But it's the same thing. Proton and neutron, you got 1s, okay? I believe, sorry, this is 4s1. Okay? Same thing, 1s, 2s, okay? And that's it, 1s, 2s, right? 1s2, 2s1. You see, they all have the s1 as common, but there is an extra whole orbital, okay, between the nucleus, and so this is shielded further. This s electron is shielded further from the nucleus than this electron, which is almost on top of the nucleus. This is only just a little bit further. So the more shielding there is, more shielding, bigger size. That makes sense, right? Okay. More closer you are to Earth, the higher the gravity. The further you are, like in Moon, there's no gravity, right? So you float, here in Earth you stand, right? That's the difference. This one s electron is shielded by this many in front, okay? Whereas this is only shielded by just this. This is only shielded by nothing. Actually, it's right facing the nucleus. And the more closer the electrons are to the nucleus, there's going to be a stronger pull. It's like the Earth's core, the gravity, and so it's going to be smaller, which is why we said hydrogen is smaller than lithium, which is smaller than sodium, which is smaller than potassium. Because by the time you get to potassium over to sodium, you always keep adding more and more orbitals in between towards the valence orbital and the nucleus This is the valence right here, right, and your nucleus is somewhere right here. So there's going to be a lot of shielding. That means it's bigger in size. So let's do a practice exercise. Nothing works better. I can talk and teach, but if you don't practice, chances are you're probably not going to get this right. All right, let's bring our periodic table back. All right, I'm going to give you some examples. I'm going to actually leave the periodic table here as I give you my question, and then I'm going to take this out and come back with my answers. Okay, arrange the following elements. Arrange the following elements. Okay, in ascending order of size. Okay, ascending order of size. What do I mean? You start with the smallest one and you go ascending order of size. Okay, so I'll give you some elements. Now here's where things get tricky. The last time we looked at, all elements were in one row or one column, but I'm going to throw elements across the board. Now all you have to still do is you have to do a little maneuvering, but I want you to try it. Okay, the rule is the same, but I still want you to be able to come up with the example: beryllium, magnesium, aluminum, arsenic, polonium or tellurium, polonium, and let's say rhodium. Okay, these are the elements that you're going to take and you're going to put them like this. Okay, actually no, let me put it this way. You're going to put it like this. So whatever is over here is the smallest, and whatever is over here is going to be your largest. All right, take your time, and then I'll come back with a different video because this requires more explanation. So I'm not going to just continue it. You can go ahead and pause it, and then when you come back, I will have the solution for this explained, and then from there we'll go to the next periodic 10. Okay. All right, you can go ahead and pause and start working on. Use the same rule, which is atomic radius decreases as you go from left to right, and it increases as you go from top to bottom. The rule still stays the same, but you have to place these things in a more unique way. All right, I'll see you back with the solutions.